Hi, we now continue our investigations using the entropy derivation and turn our attention to the calculation of average values. We have done some average value calculation in the previous video, but now we will try to make these calculations with more complicated functions. Of course, our average values are calculated just for any phase space function, which may be, for instance, the energy, is just calculate, for instance, for function g, just calculated using the usual approach of classical statistical mechanics. We just make the product of this function with the probability density function upon phase space and calculate the integral upon this space. Let's see how can we find some results related to the hydrogen atom using again Maple to find these results. Let's go to Maple to see how can we do that. Here we are in Maple. Let's call some package, Maple package, orthogonal polynomials. We can calculate here our spherical harmonics, the radial function, and so we calculate here the probability amplitude with which we calculate the probability density function upon configuration space. We can test for the normalization of these functions, it's important. This sigma here is just the fluctuation term. Note here that we are calculating it in terms of the Laplacian, of course, we are in 3 dimensions. And here we have the integral of the joint probability density function over momentum space. And here we have the integral of function f, which is our probability density function, with any function of the position and momentum, which is here represented by g. Okay, if we do that, these are all subroutines. Now we can present the function f itself by a routine using the preceding results. And of course, this is the Hamiltonian function of the hydrogen atom problem. PR is the radial momentum, P theta is the angular momentum with respect to theta, and P phi is the azimuthal angular momentum. So we can calculate for a number of states, for instance, the energy of the hydrogen atom. Let's see for the ground state first. Our density is just given by that. It's the normalized density function upon configuration space. Our fluctuation is given in these terms. We note that we have an infinity on r equal to 0, which is important to give the probability density function as 0 at this point. We also have here the probability, the joint phase space probability density function. And now we can calculate. We first test for the normalization of the phase space probability density function, which is true. And now we calculate the average energy, that is, we multiply the Hamiltonian, as given here, by the probability density function upon phase space for the state n equal to 1, ground state, and calculate the integral. This gives This gives, as we wanted, the exact result of the hydrogen atom. We can uh, repeat the same procedure for the second excited state. We can also calculate. Note that now the expression for the fluctuations is a little bit more involved. The function f is much more involved, and we now again test for its normalization. It's true, and we calculate its energy, which is nothing else but minus 1 over 2 times 2 square, which is the energy of the hydrogen atom. We can do that for n equal to 3. Let's put here m equal to 1, L equal to 1, just to find the results related to non-radial, only radial probability densities. So we have here a much more complicated fluctuation term. This function here is the probability density function upon phase space, six-dimensional phase space, and we can show that this function is normalized to 1. We just here note that we here are multiplying the probability density function by 1 and integrated it over the momentum, the phase space, and showing that this gives 1 as expected. And now we can calculate the energy related to the results. Let's see, Maple was able to do. It's minus 1 over 2 times 3 squared, which is just the energy we will get for this quantum state. Note here that when we use m equal to 1, the momentum now becomes this way. This one here is just due to the fact that we are considering an azimuthal quantum number that is different from 0. In fact, if we calculate the average phi momentum, p phi momentum, we get exactly t equal to 1, which is the value of the azimuthal quantum number. Of course, we are using here atomic units. Okay, so this is a way to calculate average moments using only the probability density function that we have found, the expression over the phase space. Phase space. Okay, now that we have shown that our calculation using the probability density function defined over phase space give the correct results, let us show that the Heisenberg inequality can be also derived from the first axiom that we have used. So the, the, the axiom was presented in this way, and we can now use the relation that we have found for the momentum fluctuation to calculate the Heisenberg relation. Of course, this Heisenberg relation here is just the integral of this term, which is this one over configuration space, and also this one, which is related to this term here. We can use a triangular inequality to pass from this product of integrals to one integral squared. And if we do that, it's easy to show that this result gives us the the Heisenberg inequality in the usual form. Of course, we are squared here. We want we can just take the square root, and this will give the usual Heisenberg relation. So we can say that the Heisenberg inequality is a consequence, a direct consequence of our axioms, which also gives us as a consequence this expression for the momentum fluctuation over configuration space. Let's go to some interpretations here. It's nice to remember here a passage from a book in statistical thermodynamics and statistical mechanics, which gives which says the following: in accepting the existence of a conserved macroscopic energy function as the first postulate of thermodynamics, we anchor that postulate directly in Noether's theorem and in the time translation symmetry of the physical laws. An astute reader will perhaps turn the symmetry argument around. There are 7 first integrals of the motion, as the conserved quantities are known in mechanics. These 7 conserved quantities are the energy, the 3 components of the linear momentum, and the 3 components of the angular momentum, and they follow in parallel fashion from the translation in space-time and from rotation. Why then does energy appear to play a unique role in thermostatistics? Should not momentum and angular momentum play parallel roles with the energy? In fact, the energy is not unique in thermodynamics. The linear momentum and angular momentum play precisely parallel roles. The asymmetry in our account of thermostatistics is a purely conventional one that obscures the true nature of the subject. We have followed the standard convention of restricting attention to systems that are macroscopically stationary, in which case the momentum and angular momentum arbitrarily are required to be zero and do not appear in the analysis. But astrophysicists who apply thermostatistics to rotating galaxies are quite familiar with a more complete form of thermostatistics. In that formulation, the energy, the linear momentum, and the angular momentum play fully analogous roles. The proper first law of thermodynamics is the symmetry laws of physics under space-time translation and rotation, and the consequent existence of conserved energy, momentum, and angular momentum functions. In fact, this is connected with our derivations in a very strict way. Look at this. In statistics and mechanics, we use the partition function, which is expressed in terms of energy, and we can calculate the average energy by just calculating some derivatives of this partition function. Of course, in this case, the partition function, the energy partition function, plays exactly the role of a characteristic function in terms of the energy. And so we can also calculate the fluctuation of the energy by means of the second derivative of this logarithm of this characteristic function, the partition function. Now we have exactly the same results, but regarding the momentum. We have here the expression for the average momentum, the second degree momentum moment, equivalent to the average of the squared energy, and here the fluctuation given exactly by the same expression we have here. So in this case, since momentum for three-dimensional situations or even other situations. This P involves not only the linear momentum but also the, the angular momentum. We have expressed here exactly the same notions that are expressed by the energy partition function, but now with regard to the momentum. And this is exactly what Kaelin, that passage I had just read, comes from Kaelin's book on statistical thermodynamics, thermostatistics, and this is, I would say, the exact formulation, mathematical formulation of what he is saying at that passage. Now we can talk about very confidently about fluctuations. We have just shown mathematically that quantum mechanics is indeed related to fluctuations. And of course, if we are talking about fluctuation, we guess that we are talking also about random behavior. But we have to get a little further in our approach to show mathematically that this is indeed the case. We may have fluctuations, but not related necessarily with random behavior. So the next step in our derivations will be to try to connect these fluctuations with random behavior, that is, to stochastic behavior. We also can see from the approach we have just made that we may probably be dealing with a canonical ensemble approach. This approach will have systems which have both particles and fields, but quantum mechanics is looking, as regard to the Schrödinger equation, is looking only for the particles and considering the field as a thermal reservoir. And this is, as we will argue in some videos to follow, that is the origin of the fluctuations and in some sense also the origin of random behavior. But of course, as with random behavior, this is simply something that is guessed by our approach so far. If these two things are true, that we have random behavior and also this kind of big canonical ensemble behavior, so most probably we will be able to connect a single system approach to an ensemble approach by means of the ergodic principle. If we can do that, we will break down the distinction in the realm of quantum mechanics between an ensemble approach and a single system one whenever the ergodic principle is appropriate. But this will have to wait a little bit until we get a little bit further in our developments by showing that quantum mechanics can be derived by other means too. So in the next video, to end this entropy maximization, entropy derivation approach, we will show that that function f q p is indeed the function that allows us to make the entropy maximization over phase space. That's it for the moment. Thanks for watching.